In this section, we're going to look at representing linear growth patterns. What that really means is, in a linear growth pattern, is that we're just increasing with a constant rate of change, and so we just usually recognize it from some model of things increasing. So, as a simple example, we want to represent the following patterns in multiple ways. So, the first set here in question A. We have 1 square, 4 squares, 7 squares, and 10 squares. And so we want to work our way through these and model this. Now, we can do this with a table. And I think the most common thought would be, yeah, okay, so this is step 1, 2, 3, and 4. But when we think about how we work with our linear relations, we need our initial value, and so where we starting is our initial value. That's going to be our 0 value, our step 0. And so this is actually step 0, 1, 2, and 3. And for any of you that have an interest in computer science and computer programming, and maybe have done some counting in that type of area, you'll find that computers start in the same place, and mathematically it often makes sense to start at 0, even though 0 isn't the regularly thought of number in human terms. So anyways, we'll start at 0. So we got step 0, 1, 2, and 3, our 4 steps there, starting at 0. And then we have our blocks. We have 1 block, 4 blocks, 7 blocks, and 10 blocks. And then we get our first differences. Again, when we do our differences, we're taking this number, subtracting this one. So 4 minus 1 is 3, 7 minus 4 is 3, and 10 minus 7 is 3. That makes sense in terms of our situation because our step pattern is going up by 1, and for every 1 we go up, we should increase the number of blocks by 3. And so our first differences relate to our rate of change. Now we want to graph this. That would be another method of representing this linear pattern. So we can represent linear patterns with tables of values. We can represent them using a graph. So if we graph these points, we have 0, step 0, and 1 block. So a point here. We have step 1 and 4 blocks. Step 2 and 7 blocks. And step 3 and 10 blocks. And so we have our points laid out, and then we'll connect the dots. And so we get a linear growth, something like this. Now, in reality, does the line make sense here? No, probably not, because we're really counting. There is no stage 1.5, but it allows us just to illustrate that it is a linear growth. Now, on top of that, we have our table and our diagram and our graph. We can also create an equation. So recall that our equations are y equals mx plus b, and we're using that one because this is partial variation. There is there's an initial value of 1 here, so that's our b value, and our rate of change, well, that is our first differences, or we can draw it on our table to determine it, and I can go say from this point to this point, and I rise 3 and run 1. 3 over 1 would be our rate of change, or just 1. Or just 3. 3 over 1, or just 3. So that's 3x plus 1 and y equals. So we can use this equation here as well to represent it. So there's 3 different ways to represent that same situation. Now, if you're given the situation, instead of the pattern, we're given, say, a graph already. So here's a graph. Step 1 has 3 items. Step 2 has 6 items. Step 3 has 9 items. And step 4 has 12 items. So the first thing we can do is represent this with a table. So we have step 1, 2, 3, and 4 here. And Why didn't I start at 0 on this one? Well, I don't have 0 listed here. I have 1, 2, 3, 4. So I'm just going to list out what specific items I have, or steps I have. So those were 3, 6, 9, and 12. And then again, when calculating our first differences, we skip the first one, and then it's 6 minus 3, which is 3. And 9 minus 6, which is 3. And 12 minus 9, which is 3. So we have a graph here. We have our table now. And again, our step value is going up by 1, so our first differences are 3. That's our rate of change. We can also represent this with an equation. And similar to the last one, we have our y equals mx plus b. Now, we have our rate of change, and we can again check that on the graph. It's over 1 and up 3 if we make our rate triangle. 1 and 3, so 3 over 1, which is 3. So that's our m value. But we don't have an initial value on the graph. The initial value is not shown there. But if we extend our graph, so if we take our graph, line it up, our ruler with the dots, and extend that back, we see that it has an initial value of 0. So this is a partial or a direct variation, so we don't need the b portion. So we can scratch that off on here, and there is our equation. We could also use our table to determine that initial value. If we're going up by 3 each time here, then we'd go back by 3 from this. 3 less than 3 is 0, and that would give us our initial value as well. It'd be back to step 0, and that would be back there. So we can use our graph to extend back to the initial value, or we can use our table in this case to do that. And so now we have an initial value of 0 and a rate of change of 3, and we've represented that graph in a couple ways. So just a couple, again, applications of using the linear relationships that we've been working with. Again, understanding things like creating formulas, graphs, and tables from information, understanding the rate of change, and the initial value portions of the formula as well are all the key concepts here.